So now we're moving to the last couple topics in the class, and it may seem a little bit, the order seems kind of strange possibly, but I like to keep sort of correlation regression and even chi-square, which are both more simple, and especially with correlation regression, something a little bit more familiar. So to sort of end the session, the semester, on a more familiar, sort of simpler note, as opposed to sort of hitting things like factorial or ANOVA and things as sort of the end, ending on a more complicated note. So we sort of hit the maximum sort of complexity, and now sort of with repeated measures a little bit simpler, correlation regression is a little simpler, and chi-square is very simple. So we sort of end on a nice, warm, fuzzy feeling at the end of the session of the semester. So correlation regression, it's all about relationships. All right, so correlation and regression are essentially the same thing, especially when dealing with one predictor. They get more complicated when you have more than one predictor of an outcome, but we're going to stick to the simple. We're going to talk about the relationship between two variables, x and y, and then we'll talk about how x predicts y in regression. So the difference between correlation and regression really just a matter of directionality. Correlation doesn't have a direction. I mean, regression does. But it's still really talking about relationships. So I just was joking here, it's the kind of relationships your mom never warned you about. So these are relationships between variables and how we can use that information to test hypotheses and things. And even though a lot of focus is on things like factorial ANOVAs, like the 2x2 ANOVA, in a lot of research where things are manipulated, a lot of information, a lot of hypotheses are tested using correlation and regression, because oftentimes we're interested in trying to understand how things go together, how things relate. And with something like a experimental design where we're manipulating things, we're trying to see if we can affect change in things. Well, with correlation and regression, we're just trying to understand how things relate. So even though correlation and regression can't give you the, so causal conclusions and things that experimental designs do, it gives us lots of information about the kinds of things that relate to one another. And most hypotheses in psychology, and I think in probably a lot of fields, begin as correlational regression type hypotheses that then grow into more scientific, more experimental sort of versions that get tested in laboratories. Okay, so my point here is not to say that correlation regression is sort of less important because it doesn't relate to sort of experimental design. I think actually a lot of the progress moving forward in research begins and is in part defined by our ability to test correlational and regression prediction type hypotheses that then lead to more experimental designs. So these are just as important, especially in things in like fields like clinical psychology, where we're trying to understand how one thing predicts something. Well, if we can do that, then we can figure out a way to try to intervene and stop things. So if we know that childhood trauma predicts later psychological problems like anxiety or depression, well, knowing that those things are related, now we didn't experimentally manipulate childhood trauma or something like that, but knowing that those things are related, that one predicts the other, then lets us know that we can, the kinds of intervention, kinds of things we can expect, and the kinds of interventions we can actually do to help those things. So sometimes correlation regression, can give us all the information we need to do a good job in terms of being a clinical psychologist or in other fields that are related, without necessarily having to have the experimental designs attached to it, even though those are also important and give us more sort of causal information. Okay, so they're both important for different reasons. Oftentimes correlation regression are more early stage hypothesis testing stuff, but not always, that leads to experimental designs, but again, not always. Okay? And certain things that can be tested experimentally and are going to have to be tested with correlation and regression type models. Okay? So the major points here are talking about correlation is what kind of questions are answered by correlation? What can you do with it? What kind of things I want to know using correlation? Talk about scatter plots, which I hope you are familiar with from high school or previous courses. And of course, we'll go through an example. we'll talk about the correlation coefficient, and then we'll talk about hypothesis testing with R and how to test for significance. For regression, we're going to take what we know about correlation and then turn that into sort of regression coefficients like the slope and intercept, and talk about how we can do predictions and talk about residuals. But I'm not going to go too much into detail about hypothesis testing with regression, mainly because of time, but also just because of some of the complexities that come out with trying to test the slope and intercept values for significance. And we just sort of leave it alone that if the test for the relationship is already sort of in the correlation. So if you test the correlation and then find the prediction coefficients, that'll give you sort of an idea of sort of how they are related and how you can predict. And we'll talk a little bit about residuals and how we can measure the quality of the prediction. But then we're going to stop just short of sort of talking about hypothesis testing, like actually doing significance testing with the coefficients, and we'll sort of leave that to the correlation. All right, so we'll start off with correlation. So the main thing here is with correlation, all we're really asking is, are two variables related? We don't care in what direction, we don't care how they're related, we just want to know if they are related. Now, they can be related for a number of different reasons. They can be related because they're both related to a third variable. They're related directly. One could cause the other. One, all kinds of things could be happening. But we don't care about any of that stuff. All correlation is doing is asking, is there some relationship between the two variables? And that is it. Okay? So, are two variables related? Does one increase as the other increases? So we want to know, something like skills and income, right? So we hope that something like skills and income relate, that they're sort of positively or directly related to one another, that the more skills you have, the better you are at a thing, the more you should get paid to do that thing, right? Your income should be higher. So skills and income should be related. Another question is, does one decrease as the other increases? So if things like health problems and nutrition, so you hope that if your nutrition improves, you start to eat better, eat healthier, then your health problems should go down. And vice versa, that if you start to eat worse, your nutrition, your healthy eating sort of goes down, you expect your health problems to increase. So these are sort of in opposition to one another. They move in opposite directions. Sometimes this is called an inverse relationship, or this is really asking more of a direct relationship. This is asking more sort of an inverse, not necessarily indirect, but inverse. It's sort of they're going in opposite directions. And then another thing is sort of how can we get a numerical measure? So I want to know, yes, I want to know they're related, but I also want to be able to measure, to quantify how much they relate and in which direction. So we got two different types of correlations. So I mentioned this a second ago. Sort of there's like a direct relationship versus an inverse relationship. So here on this side, on the left, is a direct relationship where you see this is as an average number of hours of video games per week. So this amount of video games played per week, and that's being correlated with the average number of alcoholic drinks per week, so that you can see that the more hours of video games being played, the more alcoholic drinks are being consumed. So there's a direct correlation. As hours of video game play go up, the hours of alcoholic drinks also go up. And it's not perfect. It's not like a one-to-one, but you are seeing that this general from the lower left to upper right sort of pattern like this that indicates a more direct relationship, that both are moving in the same direction, they're both going up at the same time and down at the same time. On the other hand, this one is the same thing. It's average number of hours of video games per week, and this is sort of exam score on this side. So you see as average number of video games go up per week, in this direction, the value for the exam score actually comes down. Again, it's not perfect. It's not like these people down here are getting zeros or something. It's just that there is a general upper left to lower right pattern like this, where that as this is going up, this is going down. Okay. I mean, you're thinking about here, you got this person, what, 15, 16, this is like 17 hours of video games per week. I mean, over here you got people that are playing, you know, here's what, 22, 23. I mean, you got people here on this side that are, you know, they basically have a part-time job playing video games, working 20, you know, playing something 20 hours a week. You know, here not quite at that point, but you know, you're getting close to basically a 20-hour a week sort of gig just playing video games, which is likely taking away from the fact that you time studying, right? Which is why it's impacting that. Now, this is made up data, but it feels sort of true. And I'm not being judgy either. You know, I play video games my whole life from the time I was a kid, playing, you know, the simple things like Atari and those things when I was younger, all the way up to, I mean, my son, who currently is 14, and I sort of still play, you know, PS4 games and stuff together. I don't do it as often as I would like to, but things get in the way. So this is not me saying, oh, playing video games is bad, but there does tend to be a thing where we're spending more time doing something like video games. You're probably not spending as much time doing things like studying for exams. So direct, oftentimes this is called a positive correlation, right? Because they're both going in the same direction. This one's considered a negative correlation because of as one goes up, the other goes down, sort of inverse relationship we have here. So let's talk about an example. This example is old. It's from 1987, but I like it because it's a different view of data. It's not talking about individual people as our points, which typically is what we think about. In psychology, we often, especially in American psychology, we tend to focus on the individual person. This one's different. It's actually 21 different countries. So in 1987, these two researchers, Landwehr and Watkins, did a study where they looked at 21 developed countries. And I don't even want to get into to that whole conversation about what is developed country versus not or whatever. But they looked at 21 countries in 1987, and they looked at their data on the amount of smoking in those countries and the amount of heart disease in those countries. So this is data just reported at the country level. So not looking at individual people, we're looking at the countrywide data. So now each country is our participant. All right, so we're looking at an individual country as our subject in our data, which is different than what we talked about before. So we can look to see, all right, well, is smoking and heart disease related in these countries? So the data, you know, if you actually went and found that actual 1987 paper, the data is a little bit more, it's reported with more, you know, specificity. There's you know, decimals and things. We sort of just rounded everything up just to make things a little bit cleaner, a little more convenient. And but the results, the correlation things were not affected. We pretty much got the same results regardless. So here is the data. All right, so here's the country 1 through country 21. And in 1987, all right, which sounds like a long time ago, but it wasn't that long ago. I mean, I'm not that old, you know, but I can remember 1987. But, you know, again, that was quite a while ago. I mean, it's 2020 now. So that's 33 years ago. So it's not that long ago. 33 years ago, I'm doing that math right. Yeah, 33 years ago, the United States was the first country on the list. So country number 1. We had the highest cigarette consumption and we had the highest deaths. These numbers may seem small, but the way this is measured, the cigarettes it's 11 cigarettes per adult per day. So this is an average. So they looked at the amount of smoking in the country and they figured out there were 11 cigarettes per adult per day. So that includes people who did not smoke. So there's lots of zeros, right? But when they averaged it out, for the entire country, they found that people are smoking 11 cigarettes on average per adult per day. And then they found there were 26 deaths from coronary heart disease per 10,000 people. So this is a strange measure. It's not 26 deaths. It's 26 deaths per 10,000. And the reason why is that these different countries have their different sizes, right? So you can't just look at the number of coronary heart disease. You have to control it somehow. So for every 10,000 people, they had 26 deaths. Right? So larger countries obviously had more deaths, but they still had the same amount per 10,000. Right? Does that make sense? So these have been sort of averaged out. The rates have been sort of leveled, so that regardless of the size of the country, these numbers all mean the same thing. Right? So higher numbers are bad, lower numbers are good. Okay. Now, smoking is not the only thing that contributes to coronary heart disease, but they try to look at how much cigarettes and coronary heart disease sort of relate in these 21 countries by looking at the average cigarettes per adult per day in those countries, and then the mortality is measured by the number of deaths per 10,000 from coronary heart disease. So we can actually graph all the points. Every red dot you see on this is a country. And if I go back a second and say, all right, for the United States, let me put this way again. For the United States, 11 and 26. That's the 11. That's the 2 points. This is the X. We're going to use cigarette consumption as the X axis, coronary heart disease as the Y axis. So let's find where the United States is. So we need a country that has 11, right? So we need 11 here, and it's got to go up to 23, which is there. So here, this is the United States. Okay, so here's the U.S., good old U.S. of A. All right, this is the U.S. there. Okay, and we can look at other ones. So like the one I happen to point out here is I can go up from 6 cigarettes per adult per day. Okay, now there are 2 countries. We have there's 2 countries, country 8, country 9. One country has, they both have 6 cigarettes per adult per day, but one has 11 and the other has 23 deaths per 10,000. That's a pretty big difference. And by the way, I think I said 23 before. The U.S. is 26. So I guess that looks right, because this is 20, 25, somewhere in the middle, just about 26. All right, so this is the U.S. for sure, with their 11 cigarettes per adult per day and the 26 deaths per 10,000. But then, so this particular dot here is got to be the country that has 6 and 11, which is, so 6 and 11, so it's country 8. Whichever country 8 is, they have 6 as their average cigarette consumption per adult per day, and 11 deaths per 10,000. That's the point being represented by that point there. The other country that had 6, an average of 6 cigarettes per adult per day and 23 deaths is located up here. So you can see there's a pretty big difference. These are 2 countries with the same amount of smoking on average. They have very different, very different values for the number of coronary heart disease deaths. Okay. So each one of these points represents a country on the list. The line I put in there, we're going to talk about the line later when we get to regression. It's just here to give us a general idea that there is a movement from the lower left to the upper right, telling us there is at least a positive direct relationship between smoking and coronary heart disease in these countries. So let's talk about how correlation works. And I love this little thing up here. It's like, I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. Anyway, that's a little, sometimes you got to try and find the stats human where you can. But, so let's talk about correlation. So the idea behind correlation is that we're trying to find the correlation between variables. So it's the relationship between 2 variables measured with a correlation coefficient. Most popularly used or seen correlation coefficient, something called the Pearson product moment correlation, or the Pearson correlation, which is basically the correlation that was developed to find the relationship between 2 continuous variables, which is what we're working on here. The idea of cigarette consumption and coronary heart disease deaths being a sort of continuum, a continuous variable, 2 continuous variables. Pearson makes sense. Okay. So again, I mentioned this before, the types of correlation. We talked about direct and indirect, but some other names for them when it comes to looking at the actual coefficient is if you start in the middle here at 0, right? So there's basically no relationship because there's really no pattern, right? Sometimes high scores on X go with low scores on Y. Sometimes high scores go with high scores, right? So it's basically, they're just scattered out in sort of a boxy shape. There's really no relationship. As you move up to a positive 0.5, you can see that the points start to line up, right? Going from, again, lower left to upper right makes this a positive 0.5 correlation. And as it becomes a little bit even more correlated, 0.8, 0.9, 1, they're lined up perfectly on a line, right? So at a 1, there's a perfect one-to-one correspondence between the two variables. And you're getting it lined up almost perfectly on this straight line from lower left to upper right. As you go from 0 and move to negative, a negative 0.5, again, you're seeing the same kind of pattern, just going in the opposite direction from upper left to lower right. Okay, so that's going from upper left to lower right because as the X is getting larger, the Y is getting lower. So negative is that sort of inverse relationship we talked about earlier. So as it gets even stronger, 0.8, 0.9, all the way to 1, it starts to line up perfectly on this line. But one thing to keep in mind is a negative 0.5 and a positive 0.5 both indicate that the variables are equally related. A negative 0.5 and a positive 0.5 tell you that the variables are equally related. It's just that the negative is in the opposite direction as the positive. So a really easy type of test question is, which correlation is the strongest? And you'll have like 0.6, negative 0.3, 0.7, negative 0.8. And people want to pick the 0.7 because it's positive, but really the negative 0.8 represents a stronger correlation, right? Because the number, the value tells you how correlated they are, how related they are. The sign simply tells you which direction. Is it a direct sort of positive relationship or an inverse negative relationship, but the number tells you how related they are. So don't be tricked by the negative positive being sort of higher or lower. It just tells you the direction. So let's talk about the correlation coefficient, which is a measure of the degree of the relationship. It's a way of quantifying how much these variables relate. It falls between 1 and negative 1, which is, again, another good test question. If you compute the correlation between X and Y and you get 1.3, what happened? The answer is you made a mistake. You can't actually have a correlation that is larger than 1 or lower than negative 1. The sign refers to the direction. The number refers to the degree of relationship. It's based on something called a covariance, which we're going to talk about in just a second. Now, you should be able to see that there's variance in there. So covariance really just is talking about how much variables vary in a way, how much they share their variation or share their variance. So a measure of degree to which large scores on X go with large scores on Y and small scores on X go with small scores on Y. So think of it as variance, but with 2 variables instead of 1. And what does that mean? How do you have a variance with 2 variables instead of 1 variable? It doesn't even make any sense, right? Well, let's think about how we can do that. So let's remember that variance is, right? So we've talked about variance a number of times. We talked about it we talked about descriptive statistics early on. We talked about it in terms of the analysis of variance. And we sort of defined it in different ways of the variance between groups and within groups and total and all this other stuff. Let's go back to the simple version where you have each individual around a mean. So take an individual score, subtract the mean out, square it, and do that for every person and sum all that up to get a sum of squares up on top. We divide that by our degrees of freedom and we get a variance. Okay, so sum of squares over degrees of freedom, like it says down here, sum of squares, degrees of freedom, we get a variance. Great. But how do we have another variable involved in there? Well, another way of thinking about this is instead of squaring, right? So xi minus mx squared, it's really just taking it and saying, all right, I want xi minus mx times xi minus mx, right? Just multiplying it by itself. Each time I take a deviation, I multiply that deviation by itself. That's a way of sort of squaring, right? Or if I look at it this way, xi minus minus mx, I could switch out for another variable here instead of actually just multiply it by itself, instead of squaring. I can take and sort of switch something out there. So what I could do is think of the sum of xi minus mx. Awesome. But what if you traded one of the x's out for a y? Well, I can say, all right, great. It's like sum of xi minus mx times yi minus my. I notice there's no square because I'm multiplying by itself. And I can divide that still by n minus 1. That would give me a covariance between x and y. So it is very much set up like a variance, but instead of taking the deviation around one variable and squaring it, I take the deviation for one variable and multiply it by the deviation for another variable. Do that for every single person and add them up. So instead of being a sum of squares on top, because we're multiplying, which is we're finding the product of these two, this is now called the sum of products, SP instead of SS, over degrees of freedom. Degrees of freedom stay the same. So now we're talking about sum of products instead of sum of squares. So if we actually had two variables and we wanted to relate them, I can simply take the deviation for person number 1, take the deviation around the x mean, times the same person's y score around the y mean, multiply those together, go to the next person, go all the way through every single person, finding the two deviations and multiplying them, and dividing by a degree of freedom. If I sum all that stuff up, divide by a degree of freedom, I get a measure of the covariance between x and y. All right. Sounds good, I guess. But what does that do for us? All right, how does covariance help us in any way? So again, so here's our covariance, right? xi minus mx times yi minus my. Sum all that up for everybody across all the respondents, participants, divided by n minus 1. We get a covariance. All right, so here's what we're going to think about. So what does this do for us? How does it work? When would an individual person have a positive value for x for the covariance of xy? So we got to think. So each person is going to be contributing to some part of these products, right? They're going to have their product summed up. So when would a person's score be positive? All right. If in order for a person's score to be positive, I would need to have a positive number here times a positive number there, right? So a positive times a positive would mean that I would contribute to that sum of products, I would contribute a positive number. But I could also have, it also would work if I had a negative number here and also a negative number there. So as long as they're both negatives, when I multiply them, it becomes a positive, and I would still contribute positively. All right, well, when would a person's contribution to that product be negative? Well, if this is positive and this is negative, or this is negative and this is positive, when the two signs are different, then a person would contribute negatively. So one way to think about this is, when would stuff be positive or negative? So let's think about this for a second. I'm trying to make a visual. I have my x and I have my y. Whatever these variables are measuring, it doesn't make a difference what the score, what their scales are, doesn't matter in that stuff. But what does matter is, whatever this is, I'd say this is the whole variable. And maybe y is even a little bit more truncated. It's not quite as variable as it is, but somewhere in here, there's going to be, x is going to have a mean. Right? Somewhere in there is going to be the mean of x. Mean of x. Right? And And somewhere on y, there's going to be a mean for y. So we're going to have our means. Have a mean for x, a mean for y. So in thinking about these being positive or negative, let's say my score is here. Okay, there I am. And if my score on x is above the mean on x, and it's also above the mean on y, I'm going to get I'm going to get a positive here and a positive there. All right? Make sense? It also makes sense that if I'm below the mean on x and below the mean on y, I'm going to also contribute a positive product, because if I am below the mean on x here, I take my score minus the mean, I'm going to get a negative number. And if I'm below the mean on y and subtract the mean, I'm going to get a negative number. So I multiply those two, I get a positive. So as long as I am on the same side of both means, right? I'm both above both means or both below both means, I'm going to contribute a positive product to the sum of products. All right. What about negatives? If I am above the mean on x, right, but below the mean on y, that's going to give me a, look up here, if I'm above the mean on x, I'm going to get a positive number, because x minus the mean is going to be a positive number. But y minus the mean is going to be a negative number, because my score is below the mean. So a positive times a negative, I'm going to have a negative contribution. My product's going to be negative, so I'm contributing to the sum of products a negative number. Well, what about, what if, again, if I'm below the mean on x, but above the mean on y? Maybe I'm way up here. Same thing. I'm now going to have, instead, I'm going to have a negative number here and a positive number there. So my contribution to the product is going to be a negative number. All right, so what does all this mean? So the way in which these products actually work is to tell us somewhat about where people are relative to both of the means on the variables. So if people are on the same side of both of the means on both variables, either both above or both below, they're going to contribute positive numbers. If enough people do that, we're going to get a positive covariance. On average, people are contributing positive products. So we're going to get a positive covariance. So it means to tell me that high scores go with high scores, low scores go with low scores. So positive covariance tells me that there is a direct relationship relative to the means. They're both above, both below, and when we average that out, there is an average for that sort of tendency. In the same way, if there's a tendency for people to be above the mean on one and below the mean on the other, and vice versa, relative to their two means, below the mean here and above the mean there, if they tend to be on opposite sides of the mean, and we do that for enough people and get an average, we're going to get a negative covariance, that there's a pattern. There's a pattern for people to tend to be on opposite sides of the means on both the variables, then we're going to get a negative covariance. And it tells us that high scores on one go with low scores on the other, low scores on one go with high scores on the other. All right, so it's all relative to the mean and sort of where you are. And looking at sort of an average product across all people, if the average tends to be positive, it's more of a direct relationship. The average tends to be negative, it's more of a inverse or negative relationship. Okay. So I thought this was a correlation chapter. Why are we talking about covariance? What does this do for us? We're getting there. Covariance is sort of a step in the right direction. It's just hard to interpret. Now we can look at the signs, positive, negative, but the number we get for covariance tends to be a little strange. It's hard to interpret in and of itself. Let's look at that. What do we mean by covariance? What does it actually do? So like I said, the covariance actually is sort of hard to interpret. It's numerically a little strange. The positive negatives helps, but what we can do instead of sort of trying to interpret the covariance directly is we can try to standardize it. The same way that we standardize scores, raw scores into z-scores, we can take our covariance and standardize it. How do we standardize things? We tend to divide by standard deviation. We take things, divide by standard deviations to standardize them. We did that with Cohen's d. We subtracted the means between the two variables, and we divided by a standard deviation to standardize the difference. Same thing. So a Pearson product moment correlation basically is symbolized by R. It's basically just the covariance divided by the product of the two corresponding standard deviations for our two variables. So if we take a covariance divided by that product of the two standard deviations, we can standardize the covariance and make it into a correlation. Where here we now have these restrictions where the lowest number is going to be -1, highest number is 1. All that stuff sort of applies because we standardize it using these two variables. Okay, so a correlation is just a standardized covariance. Covariances are great at sort of getting us to a correlation. Again, they're just hard to interpret beyond just the signs, and the correlation helps us to interpret sort of whether they're big or small or large or whatever. So let's talk about how to do this. Let's actually go back to our example and look at how do we actually compute all this stuff and interpret it all. So to do that, we're going to be able to test the correlation, be able to see the correlation is significantly large. So in terms of magnitude, how big is big? How big a correlation do you have to have before you can consider it a substantial correlation? The problem is small correlations in large samples could be quite large. Right, even though they're small numerically, because they're coming from a large sample, it can actually be sort of meaningful. Same way, large correlations in small samples could just be a random variation, a random sort of noise that we're getting in there. And it may not mean very much at all. So our conclusion about the correlations really depends on the size of the correlation, but also the size of the sample with which they've been measured. So it depends on the magnitude of the correlation coefficient, but also the size of your sample is going to impact that and how we make a decision about whether or not it's a significant correlation or not. Okay. So this goes back to, I mean, this is nothing new. The same thing with a t, when we talked about t's and f's, the bigger your sample, right, the easier it is to find a significant f. Your f comes down, so you can find something more significant with a smaller f value. The smaller your sample, the larger your f criticals, right? So it's the same idea that we need to be able to use the size of the correlation, but also find critical values for R based on the size of the sample so we can actually test it. So let's talk about our hypothesis testing steps here. All right, so you can sort of see those. Step 1, step 2, they're a little dark, but I think they're visible enough, I think. So step 1 is we're going to find, we're going to state our null and alternative hypotheses, just like before. Nothing's changed. They're going to do the 7 steps. The thing here is that there's actually a new bit. So when we talk about null and alternative, we always state them in terms of population parameters. Right, so we've not talked about a population parameter for correlation. So we're going to be testing R, which is our sample value, versus rho. This is the Greek letter rho. So our null is going to be that rho equals 0. So this is what's called the test of linear independence. Right, so if my correlation is 0, it means the variables are not related. So that's what it means. If rho is true, and we get a correlation of 0, there's no relationship between the variables, so they are independent, right? So a true null means that. A false null, if we actually reject it, means that there is some kind of relationship, but it doesn't really necessarily say which direction. All we care about is, are they related? So the alternative hypothesis is that rho is not equal to 0. So correlations, at least in this class, there are one-tailed correlation test, but I think it's sort of silly. In here, all correlations can be tested as two-tailed values. We want to know if it exists, right? If a relationship exists between the variables. So the null and alternative are stated as sort of two-tailed tests: equal, not equal. And that's what we're going to test in here. Step 3 stays the same. We're still assuming alpha is 0.05, and because this is the chapter, and when you're asked about what's the relationship between these variables, or are they correlated, you should know right away that we're doing it's a correlation problem. So step 4 is state the type of test you're doing, and we're doing a correlation. So for step 5, we need the degrees of freedom. And this is one of the places where the general sort of rules that we follow sort of get broken. And I always think this is a little bit odd, because when we go to do the covariance, right, our covariance, x and y, equals our sum of products over degrees of freedom. So these are degrees of freedom that we use to calculate the covariance. And these are actually n minus 1. We use n minus 1 because that corresponds to the degrees of freedom when we compute just a variance, right? Because we divide by n minus 1. So it makes it helps it sort of correspond, which is fine. It makes some sense. But when we go to look up an R critical value in a table, we're going to look it up with n minus 2. Not n minus 1. So now you have n minus 1 to divide by, but you got to look it up with n minus 2. It's kind of a pain in the ass. The reason for the n minus 2 is when we're looking at correlation, we have two variables. There's an x and a y. They both have means. And we need those means to calculate the covariance, right? So we look up the degrees of freedom in a table with n minus 2 because we lose one degree of freedom for the mean of x and 1 degree of freedom for the mean of y. So we end up losing 2 degrees of freedom instead of just 1. So even though we're dividing by n minus 1, we're going to look up the critical value of n minus 2. It's a bit confusing, I understand. That's just how it is. So our degrees of freedom here, because we had 21 countries, it's going to be 21 minus 2 equals 19 degrees of freedom. So our R critical with 19 degrees of freedom equals to what? Oh, and then we looked it up on an R table. So the R tables are just attached to the same list of tables you have on Canvas, so it should be there. So it looks like this. The significant values of the correlation coefficient. Notice it does say the degrees of freedom are n minus 2 when you look this up, so it does remind you that that is true. Let's look at it a little bit more. Okay, so again, we want the two-tailed test. We want alpha equal to 0.05. So we're going to scroll down to 19 degrees of freedom. Here, 0.433. Okay, 0.05. N minus 2 is 21 minus 2 is 19. So 19 is our degrees of freedom. And we find the critical value is 0.433. So our R crit with 19 degrees of freedom is 0.433. That's from the table. So then our decision rule is if R observed. Now remember, we could think of this really as it's two tails. Really, it's like the absolute value of R observed, whatever that is. If that's greater than 0.433, we're going to reject the null hypothesis. Remember that null is linear independence, so we're going to reject the linear independence hypothesis, meaning we think there is some relationship. They are not independent. All right, so now we go on to step 6. Step 6 is where we actually compute. Just like at any other step 6 we've done, this is where we actually do the actual observed. We actually find here the R observed value. From this, we need to compute the sums of products. We need to divide by n minus 1 to get the covariance. Remember, this is the covariance equation here, right? And then once we have the covariance, we're going to divide that by the product of the two standard deviations to get R. So covariance over the product of standard deviations. All right, so first calculate the covariance, convert that to a correlation, and then we can compare the correlation to the critical value of the correlation we just had in our last slide. All right, so let's talk about that. So to do this, there's lots of different ways of doing this. I just did it this way in a table because I figured actually it would be a little bit neater than trying to write it out in a sort of linear fashion. Okay, so what I have given you here is here's all the individual X scores, all the individual Y scores. And then down here are the means for x and y and the standard deviations for x and y. So all that stuff is given to you as part of this. So the way we're going to find this is for each person, we need to find the deviations they have on both x and both x and y. So that means that up here, on the top, for instance, I want to make this is going to be our sort of x minus mx column. And then I need to make a y minus my column. So for the first person, or first country number 1, okay, I'm going to take 11 minus my 5.952, because that's x minus the mx. Okay, so with my phone. So 11 minus 5.952 equals, so for the first country, their deviation is 5.048. Okay, 5.048. I need to do the same thing for that country for y. So their y value is 26. The mean for y is 14.524. So I'm going to take 26 minus 14.524, and I get 11.476. 11.476. And then I need to actually have the product here, right? So I need the product of those two. So I'm going to take and multiply. 5.048 times 11.476 equals 57.931. 57.931. So that's country 1's contribution to the sum of products. Okay, so I took how far away their x score was from the x mean. I found out how far away their y score was from their y mean. Then I multiplied those two together to get a product for country number 1. And I would continue to do this for all 21 countries. Find the deviations around the x mean, find the deviations around the y mean, multiply them together. And once I had all the products from all the different countries all the way down, I would then sum them to get a sum of products. So instead of doing that by hand, which would, I think, get messy very fast, I have it sort of prepared. So let me erase and I'll show you. All right, so here is the data. All right, so here's that 5.048 and 11.476 we just found for country number 1. Multiply them, got that 57.927. That's what I got, right? I got 57.931. This was done in Excel. I'm assuming it's carrying more decimals, even it's only showing 3, which is why this is probably a bit more precise. But anyway, if I multiply this times this, I get that. And then for country number 2, right? So they have an x score of 9. 9 minus 5.952 is 3.048. They have a y score of 21. 21 minus 14.524 is this 6.476. I multiply this times this, and I get the product for country number 2. So I've done that all the way down for every single country. And before we even get to the sum's down here, there's 222.524. Before we even get there, what do you notice? All right, so most of the numbers, especially the very large numbers, are all positive. There are some negatives. There's a negative there, negative there, negative there, negative there, another negative. But all the negatives are relatively small because these are all countries where they're both very close to the mean on x's and y. So they're not contributing very much because they're both real close to the averages for both smoking and heart disease. Okay. You have countries with very large contributions, like 31.070, because they're both on X and Y far below the mean on both the X and Y variables. So they have a very large product that they're contributing to the sum of products. So we add all this up, right? The general thing is, like, if there's really no relationship, you should see a mixture of negative and positive, especially, large positives, large negatives, all this other stuff. And this sum would be close to zero, right? Because you have a mixture of similarly sized negative and positive values, which we don't. In general, we're adding all these up and we're getting a positive number. 222.524 is our value that we get for a sum of products. So to get the covariance, all you do is take that, divide it by the degrees of freedom. So now that we have the sum of products, we can use that to find the covariance. We know from the previous page that the sum of products was 222.524. We know we have 21 countries, so I should be able to figure this out by taking 222.524 divided by the 21 minus 1, which is the part that's frustrating. Okay, so I'm taking this and dividing it by 20. So what is 222.524 divided by 20 equals 11.1262. So 11.126. Okay. 11.126. And this is the same, it's really the same thing, sum of products. I'm not going to rewrite it, it would be the same thing. So it's really just 11.126 is our answer. Okay. So now we have the covariance. And here's what I was mentioning before. I can tell that this is positive, that there's a positive relationship between smoking and heart disease. But I don't know how to interpret this. It's something like, because it's a mixture of cigarette consumption and coronary heart disease, it's like 11.126 deaths per cigarette or something goofy like that. It's really weird. It's hard to know if that's really a lot. It's sort of a tough thing to interpret, which is why we standardize it. So we just figured out that the covariance was 11.126. So now I can actually figure out, I can put the covariance of 11.126 here, divide by the product of the standard deviations here. So where do those numbers come from? Just to remind ourselves, in case you're looking around like I just didn't pull these numbers out of the air, they're here, 2.334 and 6.690, just the standard deviations provided in this table. Okay, 2.334, 6.690. So I'm just going to plug those in. I'm going to plug them in and figure out what is the correlation. All right, so 11.126 divided by 2.334, that's a 2.334, times 6.69 equals what? Okay, so I know this is 11.126 on top. What's the product there? 2.334 times 6.69 equals 15.615. No, 15. 15.615. There we go. Okay, so 11.126 divided by 15.615 equals 0.713. So this 0.713 is our correlation. Again, maximum is 1. Minimum is -1. 0 means no relationship. So we're really getting at, we're above 0.5. We're getting closer to 1. So this is actually, it's a fairly big correlation. We only have 21 countries, and yet we're getting a fairly strong correlation between the two of them. But again, I don't know if this is significant or not until I sort of look at the rest of the hypothesis testing steps. But I do know what my observed, so you can think of this as R observed, right? This is our R observed we get from our data. We can actually then compare this to our critical value and decide if it's significant or not. So the correlation, again, is 0.713. Sign is positive. Why? All right, well, just to reiterate, we know that positive means that relative to the means, scores tend to be on the same side. So countries that are above the mean in smoking are also above the mean in coronary heart disease. Countries that are below the mean on smoking are also below the mean on coronary heart disease on average. Right? There are some countries in there individually that go against that, but for the most part, on average, that's true. Countries tend to be on the same side of both the smoking and coronary heart disease deaths means. Okay, if the sign were negative, what would it mean? So if it ended up being a negative 0.713, it would just mean that they're in the opposite. The countries above the mean on smoking would be below the mean in coronary heart disease deaths. They'd just be on opposite sides. And almost would mean that more smoking is related to less coronary heart disease deaths and that kind of stuff. That's not what we found. The main thing I want to get at, if this ended up being negative 0.713, it would not alter the degree of the relationship. They would still be as related. It's just they'd be related in an opposite direction. Okay, so again, the sign only tells you the direction, but the number tells you the amount, the degree of relationship, which doesn't change whether it's positive or negative. So in step 7, since 0.713 is our observed value is larger than our critical value we found before, that 0.433, we can reject the null hypothesis. There is evidence of a relationship between smoking and heart disease. Right? That the relationship does seem to exist in this data. At least does seem to point that as evidence that there is a relationship between smoking and coronary heart disease deaths across these 21 countries. Okay, so that's our decision. We're actually rejecting the linear independence hypothesis in favor of a linear dependency. So we're rejecting the linear independency as evidence that there is some kind of linear dependency. I think I might have said that weird. We're rejecting the linear independence hypothesis in favor of or supporting this idea that there is a linear dependency between smoking and heart disease in these 21 countries in 1987.